Okay. So a few people attending now. So yeah, right. So the first one. So I've just added a few more questions to the to the mock. So it's more of a qualitative question now on the binomial model. So it says consider a trinomial version of the one-step binomial model where the stock price can go from S0 to S0, S0U, or S0D at the final time. I meant there really, but yeah, time. So this is on Keats now, or the updated version is on Keats. I think I just put it on Keats. So if you want to look there as well. So it says, is this model complete in general, and is there a unique risk-neutral measure? Well, I think any of you who've read anything about this in the textbooks will know the answer immediately, but I didn't go into the binomial model in that much detail because I wanted to spend more time on Brownian motion stuff. But the answer is no about completeness, because I mean, if we just draw the model, there's three scenarios. So stock price starts at S0. It can now go up to S0U, stay constant at S0, although we don't have to assume that, but just for simplicity here, or go down to SUD. And I mean, it's a long time ago since we did this, but remember the whole idea. So if we're replicating an option in general, I guess we need to label the payoffs in each of the three. Yeah, actually, this is a good idea, isn't it? I can do this in blue. How exciting. Yeah. So yeah, I can put the option payoff in blue as FU, FD. I don't know what I want to call, I guess, F0 wasn't, yeah, as the other scenario. I mean, I've never had to label that before. But yeah, so, but I mean, we only have two things we can do. Remember, the idea is to hold phi 0 in the bond, and phi 1 in the stock. And you know, when we did this on the first day, I think, you know, the first lecture on the binomial model, you have to choose phi 0 and phi 1 so that regardless of what happens, usually it's only in the two scenarios, either S goes up or S goes down, the replicating portfolio consisting of phi 0 bonds and phi 1 units of stock matches the payoffs of FU and FD. The problem is now we've got the same two unknowns, but we've got three equations that need to be satisfied. So in general, and that's why if you've got only two unknowns but three equations to be satisfied, you're not going to be able to do that, apart from in some special cases, which we're not going to get into right now. So, I mean, just to remind you, you know, what equations would need to be satisfied. So, I mean, phi 0. Yeah, so I think we used to do it as the bond goes from, say, e to the minus RD. Well, yeah, okay, just let's just say that the time window is just called delta then for simplicity. The bond goes from e to the minus R delta to 1. So it grows in value from e to the minus R delta to 1 at the final. This is the initial time, that's the final time. So that makes it easy at the final time. The value of your bond portfolio at the final time is simply phi 0 because each bond is worth 1. So if the stock price goes up, the value of your replica or the portfolio that you're trying to use as a replicating portfolio will be phi 1 S0U. That would be your first equation, which would have to be equal to FU. Your second equation would be that phi 0 plus phi 1 S0 is equal to F0. And your third equation, which would usually be our second equation, is that phi 0 plus phi 1 S0D is equal to FD. So yeah, as I said, this just makes it more explicit that the fact that unfortunately we've got, as I said, two unknowns to solve three equations, and you can, if you want, I'm not sure I'll bother doing it now, you rewrite this as a linear system where you've got, I mean, well, what would it look like, at least qualitatively? You know, if you're into linear algebra, you're thinking, I mean, this is a linear algebra problem, which we essentially solved last time. It was a 2x2, you know, linear system. Now it's, I mean, you know, I've never liked linear algebra, so let me think. You've got two unknowns, but three. So what's it going to look like? It's going to look like, in matrix form, it's going to look like the unknown phi 0 and phi 1, say, as a column vector. And then it's going to be 1, and S0U. You don't have to do this, but for those of you who like linear, so that would be multiplying that times that plus that times that, which would be the first part of a general matrix multiplication, is consistent with what we're seeing there. But then you'd have the next condition as well, which would also be 1. So that we're now building a matrix here. So what S is just simply S0 and then finally S0D. So yeah, I guess this is a nicer way of writing it. That isn't. Yeah, okay. And then that. So and then that would have to be equal to the column vector FU, F0, FD. Yeah, so and it's the same thing, but for those of you who think about things in more sort of generic or canonical linear algebra terms, the linear system you need to solve would now be this, what is it, 3x2 matrix, which is this thing that we've written here, times this column vector is equal to this column vector of size 3. You know, it's what is it? It's 3 rows and one column. But as I said, in general, you can't solve that. Apart, there are special cases if this matrix takes a special form, but in general, you can't do that. This is quite an instructive question, actually. You know, in terms of it's a good workout on completeness and uniqueness of risk neutral measures. So. Yeah, okay. And then the second part says, is there a unique risk neutral measure? Well, the answer is also no, since we have some freedom now in choosing the risk neutral probabilities of going up. I mean, the condition that has to be satisfied, if you remember, again, this is a while ago, is that the discounted stock price, this is only a 1 period model, so it's a very easy calculation. The discounted stock price has to be a martingale, so the discounted stock price is S0. Remember, the discounted value just means that, yeah, okay, so I think, okay, the discount factor I used there implied that the time period was, this is just notation, was dt, not just delta. So if we want to do, but it doesn't matter, because actually when we look at the final conditions, there is no mention of the interest rate there. But yeah, if assuming a general interest rate, this is the simple equation which would need to be satisfied. Well, I guess I've taken out the factor, but there's a probability so assume that the probability of going up under the risk neutral measure is P, the probability of going down is Q, but we no longer require that P plus Q add up to 1. We obviously just require that P plus Q is less than 1. So there's an additional probability equal to 1 minus Q minus P of the stock price going to S0. So then when we calculate this expectation, well, it's probably easier to take the S0 out and put it on the inside. So S0 there, and S 0, is that right? It just says 0 there. I need another bracket there as well, don't I? So yeah, so forgetting about the discounting term, it's just the probability of going up times the stock price if you go up, probability of going down. Okay, second positive, she's probably going. Yeah, that's right. Yeah, so yeah, P is probably going up. So that, and then, but there's now an additional term, 1 minus P minus Q times simply S0. We can obviously take out the 3 factors of S0 as I originally did, and then this equation would have to be set to be equal to S0. But the problem is there's not a unique way of solving this equation. Well, yeah, let me think a bit more about that. So yeah, okay, let me just clarify exactly how much freedom we have. So yeah, so let's think if we fix P then. So if we fix P, then okay, that does fix Q, doesn't it? Because then this is just going to be an equation in Q, which we would solve. It'd be a very simple, linear equation essentially. But the problem is with that we still nevertheless have that freedom. So we have 1 degree of freedom to choose essentially the value of P, as long as obviously P. So we do need, well, we certainly need P to lie in 0, 1. I think otherwise there's no other restriction. There might be when you go for the algebra, but it doesn't really matter. But one particular case which is easier to think about is if the interest rate is 0, then we can choose any P, and then the martingale condition just simply imposes that P has to be Q because everything is kind of symmetric. So in that case, this formula simplifies to okay, is that right? I mean, if the probability of going up, oh yeah, actually, sorry, that's probably wrong, is it? Sorry, yeah, I was thinking that U and D were the same. So yeah, sorry, it's not quite as simple as that actually. So maybe I'll abandon that train of thought. Yeah, all right. So I think for now I'll just cross that out. I think what, yeah, I was thinking of the very simple case when, okay, R equals 0 and it's equal distance up to that barrier or up to this barrier or down to that barrier, in which case it's kind of intuitively clear. So yeah, okay, I mean, I can make the statement I was envisaging in my mind, which is that, yeah, if R is 0 and, okay, so, and S0 minus U minus S0 is equal to S0 minus S0D, i.e. the distance to the up barrier from the initial stop was the same as the distance down to the lower barrier, then in that case, it's very easy to check this, in the sense there's a certain symmetry about the problem, and to ensure the martingale condition, you just simply need that P is equal to Q. I mean, is that, well, yeah, I mean, you would, to check that, you would just look at, E of Q of ST minus S0, which would just be the probability of going up, which is what P times the first increment there. So yeah, S0U minus S0 plus the probability of going down times this difference in that scenario, which is S0D minus S0. But in that case, by assumption, they're the same, and that's the negative of that, or that's the negative of that. So this would be 0 in that case. So in that particular experiment, which I find instructive to think about, we've shown that the expected value on the Q of ST minus S0 is just simply 0, which of course, if you rearrange this, says that E of S, this is a martingale just in this one period setting. So I didn't ask in the question, but I just found it instructive to think about, because it gave more of an intuition. For a very simple kind of symmetric case, the intuition in that case, you can simply set P equal to Q to get a martingale model. But the problem again is still that you have the freedom to choose P. You don't have the freedom to choose Q once you've chosen P, but you do have the freedom to choose P. In the usual binomial model, we don't even have the freedom to choose. It's in the usual binomial model, there is just a Q and a 1 minus Q, and you have no freedom to choose Q. That we derive an explicit formula for Q, and there's only one unique Q that works essentially. So that's the end of that one. We did those other two, didn't we? Did I? Yeah, okay, so this one is quite a nice one as well. So, although looks like I went on the other page. Yeah, well, that's a bit annoying. Let me just rewrite that on the other page. So yeah, essentially the question is just consider a general SDE of this form. So a general drift, but a diffusion coefficient just equal to 1. That's exactly what I've got written there, but I'm just putting it on the same page. Okay, and it says find a transformation, I should say YT, to remove, which essentially gives rise to a new SDE which has no drift, i.e. 0 drift. So we can stay on this page now. So I'm looking for a YT process, which will be given by G of XT, and I need to make an intelligent choice of G. So yeah, when we apply Ito's lemon, we get that, well, if you want, we can call this dyt as well, but which is equal to d of G of xt is equal to, well, if we want to put an intermediate line in, it's G dash of xt dxt plus a half G dash of xt times whatever goes in front of dwt in the SDE, but there's nothing in front of dwt, it's just 1, so it's just simply that times the usual dt. So that's what I've written there, except I've now plugged in xt. And if we just concentrate now on the drift terms of this SDE, you can see that I've got g dash xt and mu of xt plus a half g dash xt. But I mean, in general, unless mu is of a very strange form, xt here can take any value, or at least, okay, I should probably, to be completely proper, I should probably say, is this, let's assume this is an xt that can take any real value. Of course, we sometimes look at SDEs that can only be, for instance, greater than or equal to 0, or sometimes just greater than 0. But let's just, for simplicity, assume, like the Brownian motion itself, that it can take any real value in principle. There's no obvious upper or lower bound. Then, for this to be true, given that xt could take any real value, it needs to be true that this ordinary differential equation is satisfied. So, ordinary differential equation. So, as I said, this is just me reading off g dash of x plus mu of x there plus a half gx there. So, so the funny thing about this ODE is that it has a first derivative term and a second derivative term, but doesn't actually have a term. So it's an ODE in g for the unknown function g, but it doesn't have a g term itself. It only has a derivative g. So that should. This is as far as I got in mind. I mean, that's fine, but let's just see if we can. You can integrate this, but I think it's just a messy exponential formula. But let me see if I can remind myself how to do that. So I think we would want to, some of you may be able to do this quicker than me, write mu of x equals minus a half g dash dash of x divided by g dash of x. I'm thinking that because it looks a little bit like when you got this kind of form, it's like that, except here, if of x is g dash of x. But why am I doing that? Well, I know how to integrate something like that. I know that it's natural log of f of x. So I think that's the same here. Let's just check on it. So if we integrate both sides, we won't go too far with this, but just for fun, because it's kind of, God, what have I done? A nice calculator, yeah. So let's try and compute, I don't know, an indefinite integral of this. So isn't it just, let me get back to the pen, minus a half the natural log of simply g dash of x. So yeah, I think so. Yes. So what I'm saying is the derivative of this function is this. So if we just add an arbitrary constant to that, as we usually do with an indefinite, and we integrate the left-hand side as well, I can just write the integral, I don't know, of mu. Well, okay, I can just write it in an indefinite form. Yeah, so that essentially is how you go, and then you can go further, and then you can integrate again. So you would need to mess around with, I think you'd have to choose, it doesn't really like a reference, like a special x value, and then start messing around with the actual boundary conditions to fix the C1. But essentially, this is how you would go about it. You would divide by the g dash s and recognize that that is an exact differential of this. And then you would go on. So you do end up with a formula. I think it has a double exponential and a double integral, so it's a little bit fiddly. But really, I only care about the ODE. But as I said, you can in principle solve that ODE, and it would certainly be easier in the case if mu is constant. Yeah. And you can go the other way. I think we've done this in a previous question. You can start with an SDE of this form, where there's no drift, but there is a non-trivial diffusion coefficient, and you can find a transformation to get rid of this and make it 1, but then you end up with a drift. So you either get rid of 1, or you can get rid of the drift in this thing, but you end up with a, I should say, yeah. So we've got rid of when we solve this ODE, we have successfully got rid of the drift, but now we've introduced, I forgot to say this, a Messier diffusion coefficient, which is given by g dash of xt times dwt. So so I should say, yeah, so at least one nice thing we can say is that the dyt that we get here is g dash of xt dwt And that's it, yeah. Plus no drift, because the drift, we've contrived the drift to be 0. So as I said, you kind of can either have one or two. You can either have an SD with no drift, but with a non-trivial volatility term essentially, or you can have this SD with a non-trivial drift but a trivial volatility. Of course, in general, you can also consider a general SD, but it's just that it's a transformation that can be performed in those two special cases. That's gone black, isn't it? Yeah, all right. So that's the end of that question. Don't think I added anything to that. Yeah, okay. So I added one more barrier option question, and then how are we doing for time? How many people are on the call now? That's a good question. Do we know? Just have a look. I can't tell. Maybe somebody could write in the chat how many people they can see on the call. But anyway, so yeah. So question C. This is almost just a carbon copy of what we did before. Sorry, I just literally copied this. It says the price function for a double no-touch option with barriers at L. Well, less than B. I don't know why I didn't say that. Yeah, so I should be saying here that the barrier L is less than S0 is less than SB. That's certainly implied. Oh, okay, 48. That sounds okay. Thanks to Claire, comment Natalie. But yeah. So otherwise, so I'm not asking you to derive this. Remember, it's a Fourier series formula, but it's a nice formula, albeit an infinite series, for the price of a double no-touch. And remember, a double no-touch pays you 0 if you hit either the lower barrier down here or the upper barrier here before the final time t. So this is L, say this is B, and this is your initial stop point there. That's your final time. And if either that happens or that happens, die. But yeah, or well, should probably put knockout. Option knocks out, yeah. But if you don't, if that doesn't happen, then you get to, you get your $1. So yeah, $1 and that's over 0 in those two scenarios. So everything is saying. So what's the different part today then? So it says use this formula to derive the distribution. And I mean, if you're asked to be okay, well, I should probably say maybe the distribution function just to make that a bit more precise, but it doesn't really matter. I mean, of what we call the two-sided maximum, which is the maximum of the absolute value of the final, so you look at the final, forget the word final, you look at the stock price minus its initial value at every time point until maturity, and you take the maximum of all those values. So this is one of those ones, if you see it, it's very easy. So what you do is consider not any old L value, but set the lower barrier to be the same distance below S0 as B, the upper barrier, is above S0. So the way to do that is to set L equal the distance from S0 to the upper barrier is clearly B minus S0. So I mean, as I've drawn here, that kind of is the case anyway. Well, this it looks like it doesn't. Yeah, what I'm saying is I want this distance to be the same as that distance, which luckily the way I accidentally drew it, it kind of looks like that anyway. So in that case, then we recognise that the price of the option, remember, I assume I'm setting the interest rate. Yeah, I'm setting the interest rate to 0 as I often do. Then the price of the option is just the probability that this two-sided maximum is less than or equal to the value of B minus S0. Because I mean, if the option hits B or L, and remember B, then it means that this two-sided maximum exceeded this value. In other words, the stock price ventured a distance greater than or equal to B minus S0 from its initial value of S0 by maturity. So it's really just the use of the fact that you're not locked into some particular L value. Well, you might be in a different question, but in this question, there's nothing stopping you from choosing a convenient L to answer the question. So okay, I mean, so this gives us the distribution, because apart from the slightly weird thing that we have b minus s0 there, but I mean, okay, I can just call b minus s0 little y, say, and then, well, let me think, is that any kind of problem, or is that okay? I mean, I think that's fine. I'm just thinking, is there any problem caused by the fact that we've got the b minus s0 there, so we can call that y. I mean, b is the dynamic variable, so I suppose if we want to do that, I think we need to. So I think we're all right to do it, but if we do that, then we need to replace in our formula here, which of course is the formula here. You would replace b by its definition in terms of y, which would be. So if I'm saying that b minus s0 is y, then y plus s0. So just think, because this isn't quite in the standard form of a standard distribution, because you have this difference of two things, which is a bit strange. But if we recall that y, but b is the sort of dynamic variable, because we're definitely not varying s0, but we can think in terms of varying b. So you would just take this formula, replace everywhere you see capital B. I mean, where does capital B come up? It comes up here. Capital B gives you little b, and then little b turns up there and there and there. Oh, I'm not asking you obviously to actually do any computation with it. We did a few last time when we were checking the boundary condition by looking at the sign function. But yeah, but that's essentially, so it's only a one-line answer. Well, apart from this slightly awkward thing about rewriting this in a more convenient form. So what time is it now? 21:35. Okay, so maybe I can. So I didn't. Okay, that was the whole of question 4. So what was missing? So maybe one question thing for question 3. Did I have a full question? So question 2 we had a full. Yeah. So the only thing that's missing is a single Black-Scholes question. Let me see if I can. Well, yeah. Well, while I maybe think if I can make up a question on the fly, let me know now if you have any questions about any of that. Hang about. Did we? Am I going? Oh no, we did do that question, didn't we? Yeah. So I thought. And okay. So anything else about? Maybe I just cut. Maybe there's nothing else I want to cover really. So appropriate convergence theorem. I mean, unless anyone has a suggestion, a particular thing they want me to give an example on.
Excuse me, Dr. Martin.
Oh yeah, go for it.
Yeah, well, we have the 4 questions in the final exam or 5.
Yeah, it'd be 4. So
okay.
Question 1 would be binomial model and general kind of applied probability stuff. Question 2 will be Brownian motion and Ito's lemma. Question 3 will be the Black-Scholes model, but no barrier options. And then question 4 will be barrier options and possibly other things to do with hitting times, Brownian motions, hitting barriers, that kind of thing. Yeah. So, it will look a bit like this one. It is a bit easier than this one, because it's always, when I've already set the questions for that, it's difficult for me to still have additional questions in my memory bank. So they tend to be a bit harder. It's better to have the mock that's a bit harder rather than easier. Yeah. So I don't know. Oh yeah, thanks. Yeah. Anything else? Okay. Okay. 27. Yeah. Okay. Well, I'll finish early. Like, there's nothing else that's really that I can really think that I need to cover. I don't want to completely overload you, so I'll finish there. I think were there any things I needed to correct? I think the corrections from earlier, there were only a few minor ones were corrected. Maybe there was just something here, wasn't there? So as I said, this version is already up on Keats. I think I'll just remove that and maybe add in a little bit, maybe that matrix thing, and Anything else I wanted to add in? Yeah, maybe just a few lines of that indefinite integral computation there. And what did we do for the last part? I think I was okay with that. Yeah, maybe I'll come up with a question C, but I seem to have a writer's block at the moment. I'm a bit maxed out on the Black-Scholes stuff. So that's fine. And so I'll end the is this a tutorial here? Of course, you can always go to the other tutorials where I guess they can cover what we did in this tutorial and maybe an extra question from the previous thing as well if they're comfortable with that. And otherwise, so I guess this is the end then. Yeah. So otherwise, obviously, just keep in touch by email, and good luck with the exam and have a happy and holy Christmas. Yeah. Thanks for tuning in.